Well, we have been discussing AI for climate studies, for climate forecasting, Earth system science, and so on, and it's become pretty ubiquitous. And the discussion in the mainstream media is also quite regular. You know, responsible AI, ethics, this, that, and the other thing. And there is always a question when something invades a system so rapidly, then you have to wonder whether we are being a little bit over optimistic about what it can do. Because if you keep reading news articles, it seems like AI can do pretty much anything and everything. So this is a nice caveat of a paper which says weak baselines and reporting biases lead to over optimism in machine learning for fluid related partial differential equations. That's a particular application of AI that may be producing over optimistic reactions, but climate science is actually a fluid, and it's all about partial differential equations, and we always worry about baselines anyway. Even for global warming, we are saying we are 1.5 degrees C above pre-industrial threshold, we crossed a dangerous threshold, and so on, even though we know that the baseline itself is not very solid, right? So keeping that in mind, let's read just a few points from this nice paper. There's a lot of technical details that I'm happy to confess that I'm not an expert in this, but I want to be aware of what's happening because we are using it quite a bit, right? So it's like a tool that we are using, like driving a car without knowing exactly what the details of the engine and the system are, right? One of the most promising applications of machine learning in computational physics is to accelerate the solution of partial differential equations. The key objective of machine learning based PDE solvers is, of course, to output a sufficiently accurate solution faster than the standard numerical methods, which are used as a baseline for comparison. So you do baseline standard methods, and then you do AIML based approaches, and then you compare to say it's faster, more accurate, this, that, and the other thing. We first perform a systematic review of the ML for PDE solving literature. So it's a meta-analysis out of all of the articles that report using ML to solve a fluid-related PDE and claim to outperform a standard numerical method. We determined that 79%, so 60 out of 76 papers they looked at, make a comparison with a weak baseline. Second, we find evidence that reporting biases are widespread, especially outcome reporting and publication biases. We conclude that ML for PDE solving research is over-optimistic. Weak baselines lead to overly positive results, while reporting biases lead to underreporting of negative results. So people only focus on positive results. To a large extent, these issues seem to be caused by factors similar to those of the past reproducibility crises. Researcher degrees of freedom and a bias towards positive results. We call for bottom-up cultural changes to minimize biased reporting, as well as top-down structural reforms to reduce perverse incentives for doing so. There is a bandwagon effect in every research community. If somebody says marine heat waves, then suddenly there are lots of papers on marine heat waves. If somebody says AI improves predictions, then we are applying it in all sorts of situations, and I myself am part of such a paper looking at using ML for predicting intraseasonal monsoon rainfall, claiming that we did better than the dynamic models, right? So I also have to be aware of these things. So we'll read some introductory material and brief texts from the rest of the paper and the discussion, because we will skip many of the technical details which I will not be able to explain properly, even though I read it and I have a sense of what it is and it is important, but not for this purpose of just giving you a sense of what we may be walking into in terms of being over-optimistic about interpreting ML performances for climate-related issues, which are PDE-driven systems, of course, even though we are doing it in a very non-PDE sense where we are not actually using PDE solvers ourselves. They are being used, of course, to improve models, model parameterizations, and combining models and ML to do forecasts, etc. Many fields of science have experienced reproducibility issues. In some fields, reproducibility issues are thought to impact the validity of a considerable percentage of published research. These issues are often caused by pitfalls with data analysis and statistical techniques, as well as by a systematic bias towards publishing only positive results. No reviewer will allow you to publish negative results, I guess, as these issues can undermine the credibility and authority of an entire field. They're often referred to as a reproducibility crisis. And as interest in machine learning grows, more and more scientific fields are exploring whether ML can be used to advance science. For some problems, ML has demonstrated the potential to do so, no question about it. However, there are increasing concerns about reproducibility issues in ML and ML-based science as well. Compiling evidence from 22 articles across 17 fields analyzing reproducibility issues across 294 articles, Kapoor and Narayanan argue that there is a reproducibility crisis in ML-based science. So, this paper is focused on PDE solvers, but already it's been reported that in general, across many fields, 17 fields in fact, there is a reproducibility crisis when ML is being used. Other large-scale analyses have found frequent reproducibility issues across hundreds of articles in medical ML, common pitfalls including data leakage, poor data quality, weak baselines, and insufficient external validation. In each case, pitfalls result in over-optimistic assessments about the performances of ML. In recent years, there has been interest in using ML to advance research into partial differential equations. So now we are zooming in. Scientists and engineers study PDEs because they accurately model the behavior of many physical systems, climate systems being one of the fundamental systems depending on PDEs, driven by PDEs, Navier-Stokes. Partial differential equations relate the output of a function to partial derivatives with respect to input variables, usually space and or time. Machine learning for PDE research has mostly focused on either solving well-posed forward initial boundary value problems, ill-posed inverse problems that used data to infer equation parameters or missing data, or reduced order models that learn low dimensional representations from data, right? So many applications, many forms, but all related to PDE. So ML learning for PDE. There's a lot of text here. Let me see how much is really important to read. Computational scientists have spent decades developing numerical algorithms to approximate the solution for forward PDE problems. We call these algorithms the standard numerical methods or standard solvers, which are very common. Standard numerical methods have basic trade-off between accuracy and efficiency. Computing a more accurate approximation takes more time, so often it's about time step, about resolution, implicit methods, explicit methods. All kinds of studies exist to show how we compromise accuracy and computational efficiency and speed for solving PDEs. In principle, ML could be used to learn new algorithms or surrogate models that reduce the time required to output an approximate solution compared with standard solvers. Let's say you want to do a 15-minute forecast of rainfall for a flood, but your model resolution can be so high that you are basically not going to be able to integrate forward for 15 minutes to stay ahead of the 15-minute forecast needed, because Even if you take a regional model, even if you focus on a particular region like Mumbai, you can still have lots of computational expenses. And then if you say, well, ML can do it, it looks very tempting, right? That's what is being discussed. Faster ML-based solvers could be useful for downstream applications such as optimization, inverse problem, or uncertainty quantification, and to improve or even replace the standard numerical methods used in simulation codes for research and commercial applications. So many articles, of course, have claimed ML to accelerate the PDE solutions, but these articles compare with standard numerical methods that serve as baselines and typically use data to train neural networks as components within surrogate models. So there have been many success stories reported, but in the author's view, several ways in which this success is probably limited because of already what we mentioned. To be useful, a surrogate model, an ML-based solver, must reduce the total computational cost in downstream applications. This includes the cost of generating data, training models. So now it gets into details about exactly what you are comparing. If you train the ML model and then you are integrating forward a numerical model and comparing those, then you have left out certain parts. So that's where weak baselines can come in. Secondly, ML-based solvers have important qualitative limitations that standard solvers do not share. In particular, there are serious concerns about the accuracy when generalizing to new parameter spaces, numerical stability, and predicting chaotic systems, because if there is chaos is not in the training data, then obviously ML cannot reproduce it. In our field, climate science, it could be that you don't have regime shifts in the training data or changes in El Nino, let's say, technical terms, but you can follow up on my other podcast. Then the forecasts based on ML cannot do those things because it's not in the training data. So increasing speed in a particular context cannot be the only criteria. Thirdly, one of the most widely researched methods involving ML and PDEs, the so-called physics-informed neural networks, is known to be orders of magnitude slower than standard numerical methods at forward problems, such as solving PDEs. Furthermore, physics-informed neural networks often fail to converge to a reasonable approximation, even for simple toy problems. Okay, so the results here call to question whether ML has actually been successful at solving PDEs from fluid mechanics and related fields, as the scientific literature would suggest. We identify two issues: weak baselines and reporting biases that lead to over-optimism and affect the interpretation of reproducibility of ML for PDE solving research. Okay, so reproducibility issues at present, the scientific literature has to be dealt with in this sense of reproducibility issues, and it cannot be reliable unless there is confirmed reproducibility, right? You have one paper of, let's say, we did dengue forecasting with AI, then that result looks very impressive, but you need to make sure that baseline is there, and then the results can be reproduced and also works at other places. So there are always strict tests that we have to go through, right? Let's read a bit about weak baselines. Machine learning based PDE solvers use neural networks, deep learning, and other techniques for ML to output approximate solutions to forward PDE problems. To determine whether ML can improve the efficiency of PDE solvers, ML-based solvers must be compared against standard numerical methods that serve as a baseline. These comparisons must be fair to reach accurate conclusions. A fair comparison should not overestimate or underestimate the performance of either method that are being compared. Underestimating the performance of a baseline is called using a weak baseline. In ML for PDE solving research, we observe two common pitfalls that lead to weak baselines. As a result, we introduce two rules, rules 1 and 2, that must be followed for comparison between two ML solvers and standard numerical methods to be fair. We also introduced We also introduced 3 additional recommendations for fair comparisons. However, we do not require that they be satisfied to ensure fair comparison. So it's a bit of a pedagogy about where we are going and how this has to be done correctly. What are the pitfalls then in the baselines? First pitfall is to compare the efficiency of the highly accurate standard solver used to generate the training data with that of the less accurate ML based solver. The problem is that the standard solver can be trade-off the problem is that the standard solver can trade off accuracy for runtime, and so it can also be made faster but less accurate, and so on. Okay, so what are the rules? So the rule 1 makes, so let's make sure, comparing runtime between 2 methods with different accuracies could lead, for example, to the nonsensical conclusion that a method is orders of magnitude faster than itself. Thus, rule 1 is to make comparisons at either accuracy or at either equal accuracy or equal runtime. To satisfy rule 1, either reduce the resolution and or number of iterations of the standard solver until the 2 methods have either equal accuracy or equal runtime, or a proxy for runtime. That makes sense, right? You cannot just compare high resolution model with higher accuracy to ML, which is faster but accuracy may be not the same, or it is running slower but accuracy can be accomplished. Secondly, demonstrate that reducing the resolution of the standard solver any further would give worse accuracy than the ML based solver. Some details, but you get that. The second pitfall is to compare with a numerical method that is far less efficient than a state-of-the-art method for that problem. State-of-the-art numerical methods can be orders of magnitude faster than less efficient numerical methods. Choosing the right algorithm for a given PDE can be difficult and requires combination of expertise, background knowledge, and effort. So thus rule 2 is to compare with an efficient numerical methods. Basically, when you solve a problem, you may be trying to reduce numerical diffusion, dispersion, etc. So use certain methods. So you go between efficient and inefficient methods based on what efficiency means. Could be accuracy, could be compute time, and there are other ways of thinking about this, such as smoothing out peaks, and that's numerical diffusion, dispersion, etc. So the optimization of a choice of numerical method and resolution is very complicated. Obviously, that makes baselines to be defined, very carefully and not just recklessly. So they did a meta-analysis and basically found that they could replicate article's primary outcome and achieve substantially improved performance with a different baseline. Article reported performance relative to a weaker baseline in the abstract but a stronger baseline in the results section or the appendix. So there were various mismatches in the baselines and the comparisons and the claims of ML doing better, remembering that all the papers that do that are typically going after positive results which say ML is better than standard solvers. Okay, so baseline used in some papers, baseline used implicit time stepping when explicit time stepping would have been faster. So that's what I meant by choosing numerical methods. There are reasons to choose implicit versus explicit time stepping, because implicit time stepping can allow larger time steps compared to explicit time stepping, and so on. Okay, reporting biases then. Reporting biases in an umbrella term is an umbrella term for a set of biases that can arise when the analysis, reporting, and or interpretation of research findings are influenced by the nature and direction of results. Type of reporting biases include publication and spin biases and different flavors of outcome reporting biases, such as p-hacking, selective reporting, outcome switching, data dredging, so statistical significance claims, and so on and so forth. I will not go into more details, but basically they are saying papers are not being very clear about the limitations. What they did was actually redo some of the things. So they look at specific articles and number of citations they got, starting with the top one, and then primary outcome as reported, such as up to 1,000 times faster, and then see whether rule 1 and 2 were followed and whether there was a fair comparison. So they go through. You can see some are doing well in all of them, some are failing in 2, some are failing in all. Here this says the Yang et al. Got 102 citations. It's a drastically faster ML compared to standard solver, but they didn't meet rule 1, rule 2, or they don't pass the fairness test as defined here. And there are other papers as well doing the same thing, failing all the standards being asked for by these authors. Okay, what are the limitations then? This analysis has 3 main limitations. First, the systematic review only considered forward problems and PD related to fluid mechanics. Although this is a large research area, much of the research on ML for scientific simulations was not analyzed. So exclusion criteria was used in doing the meta-analysis, which is essential. It's unclear whether these reproducibility issues are also it's unclear whether these reproducibility issues also affect research using ML for inverse problems, solid mechanics PDEs, quantum mechanics PDEs, and high dimensional PDEs. So climate science will probably fit into high dimensional PDEs. Second, we do not have proof, only evidence that reporting biases are causing negative results to be underreported. So they are they are deriving this conclusion from the meta-analysis. It's possible that other factors could be contributing to the evidence that we have presented, although we are unsure whether what those factors might be. Third, the bottom left column in figure 1, we'll look at this in a minute, is an estimate. There is also some uncertainty in the bottom center column, albeit less so, and so on and so forth. I won't read all of these, but here is figure 1. The cumulative effects of weak baselines and reporting biases on samples A and B. So you have negative results, positive results, neutral or no results. So weak baselines lead to so let's read this properly. The cumulative effect of weak baselines and reporting biases on samples A and B. Each circle or hexagon represents an article, whereas each color represents the result of comparing the relative speed and accuracy to a standard numerical method. A, we estimate that the results would be we estimate what the results would be with strong baselines and without outcomes reporting bias. In B, an example of what the results would probably be without outcome reporting bias, and see the same results in the published literature. So it's basically trying to compare what the paper claims and whether they passed the test for weak baselines and positive results, and then reporting bias, and then how the outcome would change from negative or positive results to neutral or no results in both samples. So it's a bit too schematic, but you can think about it a bit more if you want. But the main point is still the same, that you want to have good baselines and no reporting bias, negative results versus positive results, share all of them, and just set up the standards of how to compare one or the other or both, speed, accuracy, but the choices of standard solvers versus ML have to make sure that you are comparing apples to apples and not apples to oranges or apples to metal balls or something, right? So discussion, to some extent the issue of weak baseline, especially violation of rule 2, seems to be caused by 3 factors specific to this subfield of PDE solvers, forward, not inverse, a lack of domain expertise in the ML community, insufficient benchmarking by the numerical analysis community, and little awareness of the difficulty and importance of choosing a strong baseline. Although benchmarking is a critical way of evaluating model performance in ML research, numerical analysis research tends to focus more on the theoretical properties of the algorithms. So they are very, want to reduce errors, be as fast as possible, be as accurate as possible, be as stable as possible, and so on. Furthermore, the relative performance of different numerical methods depends heavily on PDE parameters and implementation details. It can be quite difficult even for researchers with years of experience developing algorithms to solve PDEs to predict the relative performance of different numerical methods on a given PDE. We have standard equations, advection, shock equations, heat and equation, a wave equation, and so on that we use, but still when you go to a real problem, that can all fall apart. Although a few researchers have begun to informally discuss issues with baseline comparisons in ML for PDE research, widespread awareness about the extent of the problem seems to be missing. To reduce the frequency of baseline related reproducibility issues in ML for PDE solving research, we make a few recommendations for best practice. Although failing to beat a baseline should not cause an article to be rejected, failing to follow best practices when evaluating models can and should be treated as grounds for rejection. First, we recommend that all articles that report using ML to solve PDEs compare against two types of baselines: standard numerical methods and other ML-based solvers. So instead of just comparing numerical solvers to ML, take two MLs as well. This allows readers to better evaluate model performance and reduces selective reporting. So there is one example that they analyzed. If other ML model solvers cannot be implemented as baselines, articles should explain why. Secondly, articles should follow Rule 1 baselines when comparing against standard numerical methods, so accuracy and speed. To satisfy Rule 1, reduce the spatial resolution and or number of iterations of the standard solver until the two methods have equal accuracy or equal runtime. This is a of critical importance, but ultimately if I am making a forecast, I will only go for forecast accuracy, and how I got there can be a little bit less critical. So for publishing, to claim that ML is doing better, you need to follow these rules strictly. But in terms of practical deliverable, if I want a 15-minute flood forecast for a 15-minute forecast of rainfall for flood management, then I'm going to use the tool that will make me, it will make it possible for me to do it and not worry about baselines, etc. Right? So you have to be careful. Articles should, in a separate paragraph or subsection, discuss how the baselines were chosen and justifying why the comparisons are unbiased, and so on and so forth. So there is a fourth one. Aside from Rule 1 and 2, we make 3 additional recommendations for fair comparisons, which is in the methods section. I'm getting a phone call which is likely a wrong number, but give me a second here. Let me pause. As I told you, it's a wrong number. Somehow my number is mixed up with some other number, I suppose. So let me go back to the PowerPoint here. Sorry about that. Oops, there's a pointer. Oops, where am I? So let's read this one. Cultural change. Okay, so I'm jumping ahead and saying how they are thinking about it. They think cultural change has to occur, but it starts at individual level, research group and or department. Machine learning researchers should have widespread awareness about and understanding of reproducibility issues. So these are broader points that I'm not going to worry about. So they also recommend some structural reforms. First, ML journals and conferences could allow for registered reports. These could be peer reviewed before experiments and so on, and Secondly, funding agencies could fund domain scientists to propose and set up challenge problems for the ML community to tackle, which could be good. If an ML expert is coming into climate, let's say Google is coming and saying we are beating all other models in predictions, but they are not climate experts. They are just treating it as a ML problem. They are taking available reanalysis and other data and training their models and then making forecasts, and nobody is worried about baselines and what exactly is being compared. So that's a good example of why you need climate community to say this is how you would test your model against ours. Okay, so funding agencies can do that. There must be a way of verifying whether or how well the problem was solved. Thirdly, the scientific community must agree that solving the problem would be a valuable contribution to science. So it's not like we are fighting against each other. We are just making sure that we are comparing apples to apples, and both can benefit from doing these comparisons and merging the methods when necessary. Like in climate forecasting, it will not be one or the other. It will be a combination of dynamic models and AI for sure. A challenge problem with these qualities would have clear evaluation metrics and either a standard baseline or no baseline at all, thereby eliminating the potential for weak baselines, reducing opportunities for outcome reporting bias, while also directing ML research away from toy problems and towards those of greatest scientific importance. So our business is a bit simple climate prediction business in the sense of just looking for accuracy in forecasts, whereas improving climate models will go in a slightly different way. If we replace the radiation module or parameterizations or clouds in the dynamic models with AI ML approaches, then we still have to have better model output, and then those models will be used for forecasting. So skill has to improve, or speed has to improve, because speed is very critical for making forecasts as well. Okay, so as I said, I'm not an expert in this, but I'm understanding all the points. Hopefully I also translated them in a way that you can understand the main points. Okay, see you in the next topic.